So let's see what happens. So I claim it will correspond to this situation here. Let's draw the normal vectors to these free planes. Okay? Well, it's not very easy to see. But, okay, so I've tried to draw the normal vectors to my planes. Well, they're all in the direction that's perpendicular to the line of intersection. They're all in the same plane. So if I try to form a box, a parallelepiped with these three normal vectors, well, I will get something that's completely flat and has no volume, has volume 0. Okay? So the parallelepiped has volume 0. And the fact that the normal vectors are coplanar tells us that, in fact, well, let me start a new blackboard. If we, okay, so now let's say that our normal vectors n1, n2, n3 are all in the same plane. And let's think about the direction that's perpendicular to n1, n2, and n3 at the same time. Okay, I claim that will be the line of intersection. So let me try to draw that picture again. So we have three planes. Okay, now you see why I prepared the picture in advance. It's easier if I draw it beforehand. And I said their normal vectors are all in the same plane. So, what else do I know? I know that all these planes pass through the origin. Okay, so the origin is somewhere in the intersection of the three planes. Now, I said actually the normal vectors to my three planes, well, that's kind of hard to draw, but are all actually coplanar. Okay, so n1, n2, n3 determine a plane. Well, now if I look at the line through the origin that's perpendicular to n1, n2, and n3, so perpendicular to this red plane here, that's a terrible picture. It's supposed to be in all the planes. Okay, you can see that better on the side screens. Okay, and why is that? Well, that's because my line, it's perpendicular to the normal vectors. So it's parallel to the planes. It's parallel to all the planes. Now, why is it in the planes instead of parallel to them? Well, that's because my line goes through the origin, and the origin is on the plane. So certainly, my line has to be contained in the planes, not parallel to them. So the line through the origin and perpendicular to the plane of n1, n2, and 3 is parallel to all three planes. And because the planes go through the origin, it's contained in them. Okay, so what happens here is I have, in fact, infinitely many solutions. And how do I find these solutions? Well, if I want to find something that's perpendicular to n1, n2, and n3, well, if I just want to be perpendicular to n1 and n2, I can take their cross product, exactly. So for example, if I do n1 cross n2 is perpendicular to n1 and to n2, and also to n3, because n3 is in the same plane as n1 and n2. So if you're perpendicular to n1 and n2, you're also perpendicular to n3. It's automatic. So it's a non-trivial solution. This vector goes along the line of intersections. Okay? So that's the case of homogeneous systems. And then let's finish with the other case. So the general case. So that means if we look at a system AX equals B, well, with B now anything, there's two cases. If the determinant of A is not 0, then there's a unique solution. Namely, X equals A inverse B. If the determinant of A is 0, then it means actually we have this situation with, planes that are all parallel to the same line. And then we have either no solution or infinitely many solutions. It cannot be a single solution. Now, whether you have no solutions or infinitely many solutions, well, we haven't actually developed the tools to answer that. But if you try solving the system by hand, by elimination, you will see that you end up maybe with something that says 0 equals 0, and you have infinitely many solutions. Actually, if you can find one solution, then you know that there's infinitely many. On the other hand, if you end up with something that's a contradiction, like 1 equals 2, then you know there's no solutions. Okay, so that's the end for today. And tomorrow we will learn about parametric equations for lines and curves.